Hey there, how's it going today? We are looking at 2.6 on transformations of functions. I know we haven't done 2.5 yet. I've decided to switch the order of 2.6 and 2.5. So we'll do 2.5 tomorrow. But today we're looking at 2.6 on transformations of functions. And our two objectives today are to be able to identify the effects of graphs by replacing the f of x with f of x plus k, or f of x minus h, or also a f of x, f of ax, negative a of f, negative a times fx, and f of negative ax. And so these are the standards that we're looking at, particularly FBF3 is where we're at, talking about these different transformations. And so a couple of definitions we need to look at first. Parent graph. Parent graph is the function of the parent function, another definition there, which is the simplest function of the family of functions. Transformations occur when the graph is slid, reflected about the x-axis, or dilated. So again, it can be slid, it can be reflected, or dilated. Those terms will come up in a moment. And we're going to get to translation in a moment, but a translation is a transformation in which the figure is slid, so there we see it again, from one position to the other without being turned. And so that's what we're going to start with, is translations. But before we even get there, we've got to talk about these parent functions. And we're going to look at 5 of them today in terms of what functions we're looking at. And so when we talk about the parent functions, we're talking about f of x is equal to some type of really simplistic function. All these will be in the form f of x. Now, of course, f of x, remember, just means y, right? And so the constant function, what is the most simple constant function we can think of? And that is f of x is equal to 0. And so remember that a constant function is just a horizontal line across the coordinate plane. And so that would be right here going along the x-axis. A linear function, remember that a linear function is one that creates a line. And so if we're looking at the coordinate plane, the most simple linear function is one that goes through the origin and has a slope of 1. And so its form would be that f of x is just equal to x. And so again, key points that the goes through the origin and has a slope of 1. For a quadratic, we're going to look at the sketch here. And for a quadratic, we're going to get the most basic parabola. Couple key features here. The vertex is at 0, 0. The axis of symmetry is at x equals 0. And our when we talk about our slope or points that we have, our first point here is at 1, 1. And then our next point is at 2, 4. And it reflects to the other side, of course, because quadratics are symmetric. And so remember, we don't talk about slope in terms of a quadratic, but we do talk about how we get from the first point to one point to the right, and that would give us what we kind of think about as the dilation factor, and we'll talk about that in a little bit in the section. And so the basic form of the quadratic is x squared. And maybe some of you are catching on to the pattern here, but we're going to look at a cubic, and a cubic's going to be kind of similar, right? It's going to be just a nice, easy cubic function going through the, you guessed it, origin. So we don't necessarily have a vertex with cubics, but we do have that change of what we call concavity, and we'll talk about that in pre-calc. But that would go through the origin again. You do have the point 1, 1 here, and the next point up here is at 2, 8. And remember, those are reflected this way with negatives. And so the basic cubic function is x cubed. Last function, absolute value, and we're going to talk more about absolute values tomorrow in section 2.5. Again, with us flipping these lessons, we're kind of getting ahead of ourselves a little bit. But remember that an absolute value function is going to look like a V. And so its vertex, we do have a vertex for the absolute values, and it is at 0, 0. And the slope is either positive 1 or negative 1, depending on which section we're talking about. So the slope of the piece in quadrant 1 has a slope of positive 1, and the piece in quadrant 2 has a slope of negative 1. And so that's the absolute value of x. And so there's our parent functions. Keep in mind the key features we talked about over here. Where's the vertex? Where's the x and y intercepts? Again, all these go through the origin. That's not always the case for every parent function. We will see some later on that don't do that. So the first of the three transformations we talk about is translations. And we can translate in two directions. We can translate in the horizontal, or we can translate in the vertical. Or we can combine the two and we get a diagonal translation, but we still talk about the horizontal component and the vertical component of it. And so this one says to describe the translation in y equals x plus 1 squared as it relates to the parent graph, and then graph the functions. And so when we talk about graphing, again, we're going to graph the parent first. So we're talking about a quadratic here that would start at 0, 0, goes through 1, 1, 2, 4, and if you're really ambitious, would go through 3, 9, and we reflect those points to the other side. Again, this is all Algebra 1 here, talking about parabolas. And so we get this blue shape here. But then let's talk about what happens when we plug in x values. So let's do a table. So we get x's, we're going to get x plus 1 squared, and that'll give us our y, and that'll give us new order pairs. And so let's just do -2, -1, 0, 1, and 2 and see what happens. And so with -2, we're going to get -2 plus 1, that's -1 squared, we get +1. And when we do -1, that's -1 plus 1, that's 0, 0 squared is 0. And when we plug in 0, we get 0 plus 1 squared, that is 1, and 1 squared is still 1. And then we get 1 plus 1 squared, so that's going to be 2, and 2 squared is 4. And our last one, 2 plus 1, that's 3. 3 squared is 9. And so as we graph these 5 new points, we're at -2, 1, -1, 0, 0, 1, 1, 4, and 2, 9. And so we get this picture. Now, remember that parabolas are symmetric, so again, this one would also come up to here if we were to continue our table. And so what does it look like this function did? Where did it shift from the blue to the red? Where did it go? Well, if I look at my vertex, it shifted to the left by 1 unit. So this is a translation left by 1 unit. And now this will be the general model. So we'll talk about the form of it here in a second. But I gotta have this +1 inside. Now, plus would normally tell us that we'd go to the right, but with horizontal translations, the x lies to you because your x is nothing good to you. And so the x lies to you, and so instead of going to the right by 1, it's going to end up going to the left 1. And so all those order pairs did shift 1 unit left. So let's look at example 1b. We've got to describe the translation in y is equal to x minus 3 squared plus 4. Now we just talked about that inside is going to be the horizontal. And we said that your x is going to lie to you. And so a -3 would normally mean that we're going to move to the left. But remember the x lies to you, so really this is going to shift it where? To the right. So now let's talk about that +4 and what it might do, because that's the key. Where's that +4 going to shift us? Now, if we had just done a function like x squared plus 4, let's talk about some x values here for a second and get some y's. So if I got like -2, -1, 0, 1, and 2, when I plug these in, so I'm going to get -2 squared, that's 4. 4 plus 4 is 8. And then I do -1 squared plus 4, so that's 1 plus 4 is 5. And 0 squared plus 4 is 4. And 1 squared plus 4 is 5. And 2 squared plus 4 would again give us 8. And so when I think about it without the +4, I would just get 4, 1, 0, 1, and 4. And so I've shifted this from 4 to 8, from 1 to 5, from 0 to 4, from 1 to 5, and from 4 to 8. So all of those are a shift in which direction? It's the upward direction. And so when we combine these two together, so this -3 we talked about was going to be moving to the right 3 units. So again, it's a translation. Right 3 units. But the +4 out back will also be a translation, but it's going to move us up 4 units. And so when we take our 5 points of our quadratic, so again, the 5 points that we graphed before, -2, -4, -1, 1, 0, 0, 1, 1, and 2, 4. We take those 5 ordered pairs, and we're going to all shift them. And so I'm going to end up right 3, up 4. So from here, right 3, up 4, ends me up there. From this one, right 3, up 4, ends me up at 5. Right 3, up 4, ends me up here. Right 3, up 4. And right 3, up 4. And so my new parabola ends up here. So again, with translations, there's 2 rules that we need to talk about. And so when we talk about it in the horizontal, we're going to take our original function, and what we're going to see is that f of x minus h, where h is the horizontal shift. Left or right. Now, when we talk about the h itself, outside of the function and outside of seeing it in the form of it, the h is going to tell us the correct direction. So if it's +3, it's going to take it to the right. If it's -3, it's going to take it to the left. But it's this minus inside that then switches the direction when we just look at a function like this example. So again, seeing this -3 here doesn't mean I'm going to the left 3, I'm actually moving to the right. Okay? And so our second one we need to talk about is a vertical. And so that's taking our f of x and putting a k at the end. Now, remember the x lies to you. So if it's in attached to the x, inside parentheses, inside an absolute value, inside a radical, whatever type of function it is. Because if you understand translations and transformations, you'll get this when we do chapter 3, chapter 4, chapter 5, all the way on. Transformations don't go away. And so the vertical translation is going to take this plus k at the end, and the k is the vertical shift. And that's going to either be up or down. Again, if k is positive, we're shifting up. If k is negative, we're shifting down. Okay? Our second type of transformation is a reflection, and a reflection is a flip of the figure along a line called the line of reflection. And so there's 2 lines that we're typically going to reflect upon, and that is either a horizontal reflection across a line of x equals a certain number, or a vertical reflection across a line of y equals a certain number. Now, when we deal with just the functions themselves, like we see here, y is equal to the negative absolute value of x, we're talking about reflections across an axis. And so we're either going to reflect across the x or reflect across the y. And so in this case, y is equal to the opposite of the absolute value of x. So again, let's graph this parent function. And so remember, that's going to start at the origin and have a slope of 1 and go in the opposite direction, a slope of -1. And so I get this V-shaped figure here. And again, we'll talk about absolute values more tomorrow in section 5. And so when we do our table, x, we've got the negative absolute value of x and y. And let's just plug in some values. So I'm going to go -1, 0, and 1. That's all you need for an absolute value. So I've got the absolute value of -1, the opposite of the absolute value of -1. And so remember, the absolute value will do its work first because it is a grouping symbol. And so the absolute value of -1 is +1, but then this -1 out back will keep us there. When I do the opposite of 0, we're going to get 0 because absolute value is 0, and 0 being negative is still 0. And the absolute value of 1 is 1, and then the negative out front will make it -1. And so when I plot these 3 points, I'm here, here, and here. And so I get this from my absolute value. And so this negative sitting out front has reflected us across which axis? It's reflected us across the x-axis. And so how we'll talk about that is if I see f of x, that's my original f of x, and then I have a negative in front, and sometimes you'll see an a put here, but I'm just going to focus on the negative in front of the function. If you see a negative in front of the function, not inside the absolute value, not inside a parenthesis or anything else, if the negative is sitting directly out front, this is a reflection across which axis? The x-axis. Okay, so again, we're reflecting across the x-axis for this case. All right, so let's look at example B. Describe the reflection in y is equal to the absolute value of negative x as it relates to the parent graph. And so again, we'll graph up our original function. So there's our parent. Our parent is just this v starting at the origin. Both sides have a slope of 1 or negative 1. And let's go to our table again and plot some values so we can see where this is going to go. And so when I plug in negative 1, 0, and 1, the absolute value of, there's a negative here, but then a negative 1 inside. So I've got negative times negative is a positive, and so the absolute value of 1 is 1. So we're going to get the opposite of 0. Opposite of 0 is 0. Absolute value of that's still 0. And we do it for 1, plugging in the 1 there. And so we get the absolute value of negative 1, which is positive 1. And so my red graph ends up being this. Now, it doesn't look like much happened here because the red is the blue. They're the same picture. But had I had a function like x cubed, we would see that what really happens is that the points that were here reflected over here, and the point that was here reflected over here. And so this is a reflection across the y-axis. And so when that negative is sitting inside the function, it's not going to reflect across the x-axis, but the y-axis. Because your x values are changing, not the y values. Okay? And so there's that. Let's look at dilation. So this is the third of 3 types of transformations. Dilations are transformations that alter the size of a figure, but not its shape. So we're not going to take a parabola and turn it into an absolute value looking function. But we will turn this into a more stretched out parabola or a more squashed absolute value. Whatever type of function we originally had, we will continue to have it. And so as we look at some dilations here, looking at example A, y is equal to 1/2 the absolute value of x. And again, we want to graph and talk about the transformation. And so again, graph up your parent first. So let's see what happens with this parent. So 0, 0, 1, 1, going up this way. Again, we're dealing with an absolute value. And remember, their slopes will be positive 1 and negative 1 on their 2 sides for the original parent function. And again, we're going to take some values and plug this in. Now, I'm going to pick some really particular values here because I want this to come out nicely. I'm going to have to multiply by 1/2. Well, if I multiply by negative 1 and positive 1, I end up with a fraction. But if I'm smart and pick even numbers, I will not get fractions. And so we get 1/2 the absolute value of negative 2. Absolute value of negative 2 is positive 2, and half of 2 is 1. We plug in 0. This is just a formality because anything times 0 is 0. And 1/2 absolute value of positive 2. So absolute value of 2 is 1, or sorry, absolute value of 2 is 2, and then half of 2 is 1. Getting a little bit ahead of myself there. And so we plot these points. We've got negative 2, 1, so negative 2, 1 is here. 0, 0, so we're still at the origin, and 2, 1. And so I end up with this new red graph going out like this. And so what this 1/2 has done, this 1/2 that's sitting in front of the function, is it has literally taken this graph and squashed it. And so how we write this out is that when we have our f of x, and we've got in front of the function, we're going to have an a value. The a is the dilation factor. So this is a dilation, and it's a vertical dilation to be exact, a vertical dilation by a factor of a. And so it takes all of our y values and multiplies them by the value that's in front. So again, if we had a value of 3, we'd be multiplying every y value by 3. If we've got a half here, we're going to multiply them all by a half, which means the y values get smaller. And so we end up, in the end, in this case, squash this graph down. And so how we write this out? We would say that this is a vertical dilation by a factor of 1/2. All right, So let's get to our last example here. We see now the 1/2 has moved inside the absolute value. And so as we graph this one up, we're going to, again, put our parent function there first. So 0, 0, 1, 1, 2, 2, and working our other direction because absolute value functions are symmetric. And so again, I'm going to put in some x values and y values here. And so again, I'm going to choose x values that are going to make this problem not be difficult. So I'm going to choose even numbers so that when they multiply, they come out nice. And so now, this absolute value being inside, we get 1/2 times -2, so that's 1. And so 1/2 times the -2 would be -1, and then the absolute value of that is 1. And then we do the 1/2 and 0, and we're going to get 0 again, and then the 1/2 and the 2, we're going to get 1, and absolute value of that is 1. Now, our brains are going to trick us here. -2, 1, -2, 1, 0, 0, 2, 1. It makes it look like these graphs are the same. And in this case, they are. But here's what really happens on the outside is we're actually not going in terms of y, we're actually talking in terms of x. So it's not that this point moved down, it's that this point moved out. We got squashed. We're getting stretched in the horizontal. And so when we see f of x and we see it with a factor inside, now a lot of times you're going to see this as 1 over b, and that's how I'm going to write it here. When you see this is going to be a horizontal dilation by a factor of b. Now, the original notes had a in it, but again, if we're inside, other books will use b, so again, you'll see those variables change back and forth. And so this problem is a horizontal dilation by a factor not of 1/2, but of 2. Because remember, it's the b that matters. Now, just for example real quick, let's say my fraction inside was 2/3. When I do 1 over b, that's just the inverse. And so we talk about the reciprocal of that fraction. So again, if my number inside had been 2/3, the dilation factor would have been 3/2. So that's the reciprocal or the inverse of the original fraction. All right, so kind of summarizing everything we've done so far. So again, this is just a summary of all the things that we've done. Horizontal translations, if h is greater than 0, so again, we're talking about the actual h value, not the sign that you see in the problem, but the actual h value is positive, then the graph is translated to h units right. And if h is less than 0, so h is negative, then we're going to be shifting to the left. But again, we're not talking about the sign that you see in the problem, we're talking about the actual value of the h, which the problem incorporates a negative into. Vertical, if k is greater than 0, then the graph is shifted k units up. And if k is less than 0, the graph is shifted h units, k units down. So as we look at reflection, we're going to talk about those a values. Remember, where is the negative? And so if the negative is outside any grouping symbol, the graph is reflected across the x-axis, which remember means if it's up here, it's now going to be down here. If the negative is inside a grouping symbol attached to the highest coefficient, the highest power, then we're going to be reflecting across the x-axis, the y-axis. And so if I've got something over here, it's now going to come over here across the y-axis. Finally, with dilation, again, if the a is outside any grouping symbol, then the graph of f of x is dilated vertically. So again, we're going to be either stretching or compressing in the vertical direction. If the a is inside a grouping symbol, and again, attached to our, and again, we could use the letter b as we talked about in the example. If our value is attached to the inside, attached to our highest coefficient or highest power, the graph of f of x is dilated horizontally. And so last example we're going to look at real quick, just identifying transformations. The graph of f of x is shown on the grid. If the graph of f of x is translated 3 units to the left, 1 unit up and reflected across the x-axis to create the graph of g of x, which function best represents g of x in terms of f of x. And so what this question is asking is not what is the new function, but where did this go in terms of our old function to our new function? And so our g of x is the new function, and what we see pictured here is our f of x. I don't care what this picture is. Now, I could figure out what f of x is. I could figure out the axis symmetry and the vertex and everything else and figure out the graph of it. But we're just saying, if I have this generic f of x here, and this is what it's telling me to do, what things are happening based on what we just said. And so when we talk about the different pieces, translated 3 units left. Remember, left is going to go inside with the x. And so I'm going to get f of x. We're moving left. And so that's going to be plus 3. Because remember, there's a minus sign originally there in the formula. Our second piece is going to shift us up 1 unit. And so when we do that, I've got my f of x plus 3. That part's not going to change. But this plus 1 is going to be plus 1 out back. And finally, our third piece is this reflected in the x-axis. And if we go back, remember the reflection in the x-axis is going to be outside the grouping symbol, or it's going to be outside our function notation. And so we're going to get negative f of x plus 3 plus 1. And so our g of x function, the one that would be transforming this function based on these steps, would be g of x is equal to negative f of x plus 3 plus 1. Okay, so again, think about each individual piece as we go through and how it would transform the function, and that's what we're looking at. All right, so I know this is a little bit longer of a section, but these are 3 major transformations that you need to know, and we're going to talk about these more as we go through the chapters. You need to know these transformations because it will help you out later on. It'll help you on the ACT or SAT. I know I hound you on that, but trust me, knowing these transformations will help you get through those problems quickly. Again, hope you listen to it all. The word of the day is transformation. Again, the word of the day is transformation. Y'all have a good one.